Hi, everyone. My name is Yonghao Yu. I'm a doctoral student from the University of Tokyo, and today I will present our work, Mirai, Autoregressive Visual Generation Needs Foresight. This work has been done with my co-authors, Lang Huang, Zerun Wang, Runyi Li, and Toshihiko Yamasaki. The central idea of this paper is simple. Autoregressive visual generators should not only learn to predict the next token, but should also learn representations that can anticipate future visual structure during training. The motivation comes from a mismatch between language-style autoregressive training and the structure of images. A standard visual AR model first serializes an image into a sequence of discrete tokens and then trains the model with next token prediction. This is strictly causal, which is good for autoregressive generation. However, the supervision at each step is very local. The model mainly receives feedback from generated tokens. For images, this is not always enough. Visual tokens depend strongly on 2D spatial structure. As a result, the baseline can generate locally plausible details, but still lose the global structure. Our intuition is to teach the hidden state to anticipate the upcoming image layout before it has to generate it. Before proposing the full method, we first ran diagnostics along three axes. First, where should Foresight be injected? Directly predicting multiple future tokens at the output level is similar to multi-token prediction, but in visual AR it introduces competing targets and can hurt performance. Instead, aligning Foresight with the intermediate representations provides future-aware supervision without forcing the model to predict multiple discrete tokens. Second, how should future positions be selected? A 2D spatial layout consistently beats a simple 1D raster scan because it respects the geometry of images. Third, what source should provide Foresight? Both explicit unidirectional EMA features and implicit bidirectional features are useful. The common lesson is that Foresight should supervise internal representations on the 2D token grid. This diagnostic study leads to Mirai, a training-only Foresight alignment framework that improves global planning while keeping inference strictly causal and cost-free. Mirai is formulated as a simple auxiliary training objective. We keep the original next token prediction loss and add a Foresight alignment loss. Specifically, an intermediate hidden state from the AR model is passed through a lightweight projection head and then aligned with a future-aware target feature using cosine similarity. The coefficient lambda controls the strength of this auxiliary signal. Importantly, this is only used during training. At inference time, the projection heads and the Foresight encoder are discarded. The AR model still samples token by token, exactly like the original baseline. So Mirai improves representation learning but does not change the inference architecture or add decoding cost. Mirai has two variants. Mirai E uses an online EMA copy of the AR generator as an explicit Foresight encoder. It aligns the current hidden state with nearby 2D positions, such as current, right, and below, providing spatially indexed look-ahead. Mirai uses a frozen bidirectional vision encoder. Since each feature contains full image context, the co-located feature provides implicit foresight about future visual structure. Both variants supervise internal representations during training, while keeping inference strictly causal and unchanged. Now let us look at the results. Mirai significantly accelerates convergence across LlamaGen B, L, and XL. Both Mirai I and Mirai E reach lower FID much earlier than the baseline. For example, on LlamaGen B, Mirai I reaches baseline 400 epoch quality with only 40 epochs, achieving up to 10 times faster convergence. This shows that Foresight alignment provides a more informative training signal for visual AR. Mirai also improves final generation quality while keeping the same AR inference procedure. Across model scales, Mirai consistently lowers FID. The qualitative results show the same trend. The baseline often produces images that look reasonable in local regions, but the global layout can be inconsistent. In contrast, Mirai generates a more complete and structurally coherent result. To conclude, we revisit autoregressive visual generation through the lens of Foresight. Our key finding is that Foresight does not break causality. Instead, when used properly during training, it can strengthen causal modeling. Mirai injects future-aware guidance into internal representations on the 2D token grid while keeping inference strictly causal and unchanged. Across experiments, Mirai improves generation quality, accelerates convergence, and leads to more globally coherent visual samples. Thank you for watching. Please visit our project page for the paper, code, and more results.